Okay, college algebra. Um, Great lesson today. It's regarding function inverses. And just want to kind of bring you back to these operations: addition, subtraction, multiplication, division. We talked about square roots, talked about, say, sine of something. We talked about the logarithm of something or natural logarithm of something. And then yesterday we brought up this new operation. It was called composition. It was that little circle thing. And today we're talking about inverse. And inverse is this, you see it listed as -1, but if I write function composition, you'd say f of g of x. We learned what that was. Well, function inverse is like that. And you see it, that -1 piece, and it doesn't mean f to the -1. This is not 1 over f. That's not what it means. We have to describe what inverse operations are. But before we talk about function inverses, we first have to understand what it means to be one-to-one. A function is said to be one-to-one if every element of the domain, so every element of the domain corresponds to exactly one element of the range. That sounds like the definition of a function, and it is. Every element of the domain corresponds to exactly one element of the range, and every element of the range corresponds to exactly one element of the domain. So, for example, if you had, say this, well, 1, 3, and 2, 5, we would say that that's a function because 1 corresponds to only 3 and 2 corresponds to only 5. But if you had this relation, say 1, 4, and 1, 6, you would say that's not a function because 1 corresponds to both 4 and a 6. So therefore, that would not be a function. Suppose we have 1, 3, and we have 2, 3. You would say that is a function because 1 corresponds to 3 and 2 just corresponds to 3. However, it is not one-to-one. The reason why it's not one-to-one is you can see the range 3 corresponds to both 1 and a 2. And so in order for it to be one-to-one, it must be like this, where each domain and range is unique to the other. Extremely important. So that's an example of one-to-one. Now, just like a function must pass the vertical line test, in order for a function to be one-to-one, it must pass the horizontal line test as well. So this function is, wait for my smartboard to catch up there. Got a little bit angry. This is a function because it passes the horizontal line test, but is not one-to-one. As you can see, the y value of 0 corresponds to 1, 2, 3 different spots. So it is a function, but it is not one-to-one. Whereas if I draw something that looks like this, that is a function, and it is a one-to-one function. It passes both the horizontal and the vertical line tests. So once you know that a function is one-to-one, we can then determine the inverse. Once we know a function is one-to-one, we can then determine the inverse. Again, function inverses, it is not this. f inverse is not 1 over f. Function inverse, the domain becomes the range, and the range becomes the domain. So x becomes y, and y becomes x. So in other words, suppose you had a function. It was composed of the point 2, 5. Then the inverse would have the point 5, 2. Suppose you had a function y is equal to 3x minus 1. Then the inverse would be x is equal to 3y minus 1. So the x and y, the domain and the range, they switch places. Graphically, they are reflected over the line y is equal to x. And we will check that out in a little bit. Let's try some examples to kind of get this through our brain. It says given f of 2 is 3, f of 1 is 9, f of negative 3 is 8, f of 4 is 5, and f is 1 to 1. Find the following. F inverse of 8. So right now, this coordinate right there is saying that if you plug in negative 3, you get 8. So when we ask f inverse of 8, it's saying if this is my y value, what's the corresponding x value? And you can see from this situation, it is negative 3. So f inverse of 3, I look for an output of 3, and it looks like the x value would be 2. F inverse of 5, I look for the output of 5. The input would be 4. F inverse of 9, I look for the output of 9. The input would be 1. So there's a little example of function inverses. Let's look at example 2. It says, given f of x is 3x minus 8, find f inverse of 6. That's a little bit more complicated. This is saying this is the y value. Are you sharpening your pencil? That's fine. You can't. Yeah, you're fine. So like, as I'm talking on the video right now, you guys will watch this at some point. Alex will be like, this is the point where I sharpen my pencil. You can only hear my voice. You can't hear you guys. So you really can't. Yeah, you probably won't be able to hear that. So f inverse of 6, that's saying that that's the y value. And then what is the x value? Well, let's plug 6 in for the y value. So 6 is equal to 3x minus 8. If I add 8, I get 14 is equal to 3x. So therefore, x is 14 thirds. So 14 thirds is going to be the corresponding x value. Let us now determine the inverses of the following functions. If f of x is 2x minus 5, the way that we determine the inverse is this. We take the y and we replace it with x, and we take the x and we replace it with y. And then we solve for y. So x plus 5 is equal to 2y, and then we divide by 2. 1/2 x plus 5/2 is equal to y. Or in other words, looks like again my smartboard did not like that. Wait for it to get caught up. There we go. Or in other words, f inverse of x, f inverse, so negative 1, f inverse of x is 1/2 x plus 5/2. There we have it. So if I were to kind of look at this graphically, which is part of what makes this unit or this lesson so interesting to me, is that we have the algebraic representation, but when we have these points, we also have the graphs. If you were to look at 2x minus 5, and then I were to also graph 1/2 x, so 0.5x, plus 5/2 or 2.5, and then I were to graph the line y equals x. You can see as I graph these, there it is. Okay, you can see the line y equals x right down the middle. The other two are reflected over the line y equals x. If you reflect the one, you get the other. And I think that's what makes it really interesting. Also, you can notice that in this situation, this has a y-intercept of -5. That means that its inverse would have an x-intercept of -5. If you look at that graphically, it does happen. Um, so they are reflected that way, which is kind of neat. Next one, a little bit more challenging. Y is equal to 2 minus x over 3x minus 4. So what I'm going to do is I'm going to exchange the x and y values. So x is equal to 2 minus y over 3y minus 4. I have to solve for y. I'm going to cross multiply. I get 3xy minus 4x is equal to 2 minus y. Gather all my y's on one side now because I'm trying to solve for y. I'm not trying to solve for x, which is something we did a few units ago. We were solving for x in this situation, but now we're solving for y. I will factor out the y, and I get 3x plus 1 is equal to 2 plus 4x. I divide by that 3x plus 1, and I have y is equal to 2 plus 4x over 3x plus 1. And that is my inverse. That's my inverse. Here we have y is equal to 2 minus 3x cubed. So I switch them. X is equal to 2 minus 3y cubed. I subtract my 2. X minus 2 is equal to negative 3y cubed. I divide by negative 3. So negative 1/3 x plus 2/3 is equal to y cubed. We cube root both sides. And we get the cubed root of negative 1/3 x plus 2/3 is equal to y. So that's my inverse. I always like to check my answers. And again, if you're going to justify your answers in this situation, if I plug in 2 minus 3x raised to the third power, and then below that, I try the cubed root, which you can do, press math. That's one way to get your cubed root button. So cubed root. Now we're going to go negative 1 over 3x, and then plus 2/3. And close that off. Let's see if one looks like the other reflected over the line y is equal to x. I guess I know I'm a nerd, but I think that that's just so cool. Yeah, our answer is verified. One graph is the other graph reflected over the line y equals x. That's beautiful. Good stuff. The next one. The next one is a little bit more delicate. This is where people start to get lost. So if you need to press pause, go grab a cup of coffee, go ahead. But then you want to lean in. And part of the reason you want to lean in is because you want to focus on this graph. You know what this graph looks like. It's shifted back 1 and up 4 units. I'm going to actually make that a little bit larger over here. Sometimes people get mad and they're like, well, it didn't say the graph. Folks, we're getting to that point where every time you see a function, you should be able to determine what the graph looks like. That's the future of math for you. I always want to know the graphical representation. And there it is. Okay? I have that vision in my mind because that's going to become important to us as we work through this. I have y is equal to 4 plus the root of x plus 1. We want to determine the inverse, we switch. So x is equal to 4 plus the root of y plus 1. Now I'm going to solve. I subtract 4. Root of y plus 1, and now I square x minus 4 squared is equal to y plus 1. Subtract the 1, x minus 4 squared minus 1 is equal to y. So you say, well, that's my inverse. And you were mostly correct, but you were slightly incorrect. And here's why. Look at what happens. When we graph that, we go over 4, and you go down 1. So just think about it. First of all, this point right there is at -1, +4. This point right here is at +4, -1. See how they switch? Exactly like we wanted it to. Good way to check your answer. But now when we graph that, that is a parabola. The red graph is not the same thing as the green graph reflected over the line y equals x. If you look at this, we got this like extra piece that just popped up out of nowhere. In fact, the blue piece is the only part that we want, but we got that extra green piece off to the side. I'm going to write extra here. We don't want it. How come we got that? As you can see, the original graph, the red graph is 1-to-1. It passes the horizontal line test. If I grab a horizontal line, the red graph passes the horizontal line test. But it produced the green graph, and the green graph does not pass the horizontal line test. That's a problem. You see, anytime you square both sides, which is what we did right in this step here, you run the risk of adding something that you don't really want. We've talked about that throughout time. So the fact is we only want the green part. We don't want, or I'm sorry, say that again. We only want the blue part. We don't want the green part. We want this green part to go away. Draw a bunch of X's on it. How do we do that? Well, we say this is what the inverse is with a specified domain. We only want it for a domain of what? If you look, the blue part is going to go from 4 to infinity. So domain from 4 to infinity. So this is my answer. Okay? This is the inverse with a specified domain. What that does is it actually cuts off that green part that we didn't want. So you have to be careful if you are working through and producing an inverse. If you come up with something that's not 1-to-1, be sure that you restrict the domain. Okay, our last part. That's the most difficult part. If you made it through that, you're good to go. Last thing we need to do is test to see if something is inverses. In order to test to see if something is an inverse, what we do is we compose them. If f composed of f inverse of x produces x, and if f inverse composed of f of x produces x, then they are inverses. So we need to compose them both ways. Okay? We need to compose them both ways. Watch what happens here. It says use the property of inverses to determine if f and g are inverses of each other. So what we'll do is we'll take f and compose g. And when we do that, that means we take this guy and we dump it right in there. And we get 3 times x plus 5 over 3 minus 5. Notice what happens. The 3's will cancel, and we get x plus 5 minus 5. And that produces x. So I'm good to go there, but now I need to compose it the other way. G of f of x. And if I take this and plug it in there, what I get is 3x minus 5 plus 5 over 3. Notice how the 5's cancel. I get 3x over 3 is equal to x. So because both produced x, it works out. You might be wondering why it produces x. Pick a value, say 2. If I plug 2 in for x, I get 2 plus, or actually let's pick 3. We plug 3 in for x. Sorry, let's pick 4. If you plug 4 in for x, you get 4 plus 5 is 9. Divided by 3 is 3. Take that 3 and plug it in here. 3 times 3 is 9, minus 5 is 4. It will always bring you back to what you started with. It will always happen that way because x is what we refer to as the identity. You know how you have an inverse of 3? We would say the inverse of 3 is 1/3, or we'd say the inverse of 3 is -3. It depends. If you're talking about multiplication, the inverse is 1/3 because when you multiply, you get 1, and 1 is the identity under multiplication. Well, if you're talking about addition, then -3 is the inverse because when you add them, you get 0, and 0 is the identity under addition. Well, in function composition, x is the identity. So just like you've learned how 1 and 0 are identities, x is an identity. Just kind of neat. All right, let's do the last two here. 3. We compose f composed of g of x. Take this guy and put it in for x. If I do that, I get 1 over, careful as you write it, 1 over x minus 2 plus 2. You have a complex fraction. We'll work this out. Notice that the 2's cancel, and we get 1 over x. We divide a fraction, we multiply by the reciprocal. So if I multiply by the reciprocal, I'll just multiply by x, and I get x. G composed of f, I take f, this guy up here, and I dump it in right there. So I have 1 over x plus 2, and then minus 2. So you can see from our previous example, when we multiply by the reciprocal, we're going to get x plus 2 minus 2. Those cancel, leaving me with x. The next one, it says for x values greater than 0. Notice how they give you something that is not 1-to-1. When they say x is greater than 0, what they did is a domain restriction. So they just cut off that part. Now it is 1-to-1. So don't worry if you get something that has a domain restriction. Just trust that it's making it so it's 1-to-1. Let's try this out. F of g of x. I take g and plug it in. I get 4 times the quantity, root of x over 2 squared. Well, that would be 4 times x over 4, which is x. Okay, great, that worked out. And now I'll do g of f of x. When I do g of f, what I'm going to get is plugging f, which is 4x squared, and dumping it into there. So 4x squared root over 2. The square root of 4x squared is 2x over 2, and I get x again. So again, the first 3 are all inverses. So we look at the last one. If you notice, the functions are the same. And when you see that, you might say right away, well, if they're the same, there's no way that they can be inverses. That's not true. It is possible that they could be inverses. Well, let's test. If you compose them, we get 1 over x cubed, or 1 over x to the 9th, which ends up being x to the 9th. That is not x, so therefore they are not inverses. And there you have it. All right, folks, thanks for tuning in. A little bit longer video, sorry. I hope you have a great day. It's a little bit warmer outside. Have a good